In this lesson, we would understand what are vector and parametric equations of a plane. So far, we have covered vector and parametric equations of a line, and we have done lines both in 2D space as well as 3D space. Here we have to remember that planes are always going to be drawn in 3D space. The learning goals of this lesson are to determine the vector and parametric equations of a plane, and to solve the problems of vector and parametric equations of the plane. Those would be the application problems. After going through the lesson, the students will be able to understand what the plane is and that the plane lies in 3D space only. The students will be able to write the vector and parametric equations given 3 points. Students will be able to determine if the given point lies on the plane when given plane's vector or parametric equations. Students will also be able to determine the vector and parametric equations of the plane given a point and the line equation. And finally, students will be able to determine the point of intersection of the plane given the plane equation, be it vector or parametric equation, and one of the axes. First, let's understand what a plane is. Plane is one parallelogram surface in a 3D rectangle-based prism. Let's say we have this rectangle-based prism. So one wall or one surface, that could be any one surface of this rectangle-based prism, is called a plane. Knowing what a plane is, we can say that when we talk about R3 space, we can always see a line in R3 space, as well as we can see plane in R3 space. Lines, their equations and applications have already been taken care in the previous lessons. From here onwards, we will be discussing plane and its applications. Always remember that plane is represented by the symbol pi. So whenever we will be using the symbol pi, that would represent the plane. Also, planes can be determined in the following 4 ways. The first one is if we are given a line and a point that does not lie on the line or lies away from the line, then we can use the line and the point to determine the plane. Second way is if we are given 3 non-collinear points. Collinear points means the points that lie in one line. These points A, B, C are called non-collinear points because they do not lie in the same line. So these points would also form a plane. Third is any 2 intersecting lines. We know the line equations. We can use that to determine the plane. Fourth is if we're given 2 parallel lines that are non-coincident, then also we can determine the plane that contains these 2 parallel lines. As we now understand what the plane is and how can we make planes, now let's go over the process to determine the equations of a plane. Equations for a plane are also of 3 types, same as the line equations. So we would have vector equation for a plane, we would have parametric equations for a plane, and we would have Cartesian equations for a plane. How is a plane different from a line is? If we remember, line equations used to be r equal to r naught with one direction vector. Whereas when we talk about planes, a plane would be r equal to r naught with 2 direction vectors. So this would represent the initial point and these would represent the 2 direction vectors. And this would constitute the vector equation of the plane. Therefore, we can say the vector equation of the plane is r vector equal to r naught plus SA, this is the first direction vector, plus TB, this is the second direction vector. The reason that we need 2 direction vectors is if we are given a point P and there is only one direction vector going from this point P, then we can't make the plane. We can only have a line. However, as soon as we know the second direction vector going from that point P, we would know that these 2 direction vectors can then constitute a plane, where the resultant vector of these 2 direction vectors, that is SA and TB, would be in this direction, which is the sum of these two vectors. And that sum is what we write down here. Same as the line vector, we can expand this vector equation. So we can split this up into coordinates. So r can be written as x, y, z equal to x naught, y naught, z naught plus s is the constant and a vector would have its own coordinates. We can say a1, a2, a3, and t being the constant again, we would have coordinates for b vector as b1. This is going to represent the x coordinate, b2, b3. We can always rewrite it as ax, ay, az, and bx, by, bz. It's up to you if you want to use numbers or alphabets. Coming to how parametric equations would look like is, parametric equations are nothing but just expansion of the vector equation into x, y, and z components. So we would write down x is equal to x naught plus sa1 plus tb1, y is equal to y naught plus sa2 tb2, and c is equal to z naught plus sa3 plus tb3. Cartesian equations we would talk about in the next lesson, because this lesson is about vector and parametric equations. Let's go over the different types of questions that can be asked related to vector and parametric equations, and how do we write down these equations. The first type of question is to write the parametric and vector equations for the plane when we are given points A, B, and C, where point A is negative 1, 3, 8, point B is negative 1, 1, 0, and point C is 4, 1, 1. As we know that when we have to write the vector and parametric equations, we would need to find out the two direction vectors. So we would first proceed towards writing the two direction vectors, considering A as the initial point. So this is, if A is the initial point, then we would have direction vector AB and direction vector AC. To determine the coordinates of direction vector AB, we would use the same procedure that we have learned in the previous lessons, and that is we would do x2 minus x1, y2 minus y1, z2 minus z1. When we solve this, we would get 0, negative 2, negative 8. Next, we would write down the direction vector AC. In this case, the 2 value goes to C, so it will be x2 minus x1, that is 4 minus negative 1, y2 minus y1, that is 1 minus 3, and z2 minus z1, that is 1 minus 8. This would give us 4 plus 1, which is 5, 1 minus 3 is negative 2, and 1 minus 8 is negative 7. Once we know the two direction vectors, and we know the initial point, we can just put this all together, and that would give us the vector equation. So the vector equation would be r vector is equal to the initial point A, which is negative 1, 3, 8, plus constant s times the first direction vector, 0, negative 2, negative 8, plus constant t times the second direction vector, which is 5, negative 2, negative 7. And this is how we get the vector equation. To get the parametric equation, we would just open this vector equation, and that would be x equal to negative 1 plus 0s plus 5t, y equal to 3 minus 2s minus 2t, and z equal to 8 minus 8s minus 7t. And this is how we get the vector and the parametric equations. Now let's say we're given the type 2 question, which is just an extension to the previous question. Here we are given a point P1413, and we are asked to determine if this point lies on this plane for which we have found the equation. For any sort of calculation, we will always use parametric equations. So how would we do this type of question is, we pick the parametric equation x equal to negative 1 plus 0s plus 5t. what we need to do is we need to find out what is the value of s and t when we use x and y of the point P. How do we get to do that is we just sub in x in here. 0s is technically 0, so we don't have to put anything here. We'll just put in 5t. So we have this equation which we can isolate for t. So when we move this over, 14 plus 1 is 15 is 5t. T is equal to 15 divided by 5, which is 3. If in case there would have been no 0 here, then we would have got the equation with two variables s and t. And in that case, we would need the second equation. And for that, we can use the second parametric equation, that is y is equal to 3 minus 2s minus 2t. We use this y equal to 1 in here, 3 minus 2s minus 2t. Here we notice we don't have any 0 with anything, so it's not that we can make anything 0. But we just got a 3 from the first equation that we can substitute in here. And when we simplify, we can get the value of s. So it will be 3 minus 2s minus 6 equal to 1. 3 minus 6 is negative 3 minus 2s equal to 1. That will give us negative 2s equal to 1 plus 3. That is equal to 4 divided by negative 2, which would give us s as negative 2. So we've got the value of s as negative 2. Now, how do we know whether this whole point lies in this particular equation or not? Since we have found the value of t and the value of s, we would use the z parametric equation and we would sub in this t and this s into this equation and solve for our z. If the z value that we obtain will be equal to 3, that means this point lies on the given parametric equation. Or we can say this point lies on the given plane for which we know the parametric or vector equation. So let's proceed further for that. Since we have z is equal to 8 minus 8s minus 7t, we'll just sub in the value of s in here. So s here is negative 2, that's what we got here. Minus 7t is 3, which is 8 plus 16 minus 21. 8 plus 16 is 24, minus 21 gives us a 3. We notice the z value that we've got is 3, and when we look at the point, we have 14, 1. These helped us to get the s and t. When we got to put this s and t in the parametric equation, we got to find out that the z we got is 3, which is also the z of the point P. Therefore, we conclude, because everything is in alignment, that this point 14, 1, 3 lies on the plane. And this is how we solve, and this is how we determine if a given point lies on the plane or not. The next type of question is type 3 question. In this, we are given a plane equation as r equal to 6, negative 2, negative 3. Plus S130 plus T 2, 2, negative 1. And we are asked to determine the point of intersection of the plane phi, this is the plane basically, and z-axis. Always remember, for any calculation, the best is to use the parametric equation. So we would first get the parametric equation from here. That would give us x is equal to 6 plus 1s plus 2t. Y is equal to minus 2 plus 3s plus 2t. And z is equal to minus 3 plus 0s minus 1t. The second step is to determine what could the point of intersection be. Now, if we are given any plane on this 3 space, we know this is the z-axis. When we make this plane and we try to find the point of intersection on z-axis, we notice because it's on the z-axis, so the point of intersection coordinates will be 0, 0, because there is no x in the y value, it's just a z value that it has. So it's going to be 0, 0, z. Just to avoid confusion with z and the variable, we could just use another variable instead. So we can use the variable, let's say C. Now the goal is to determine what is this value of C, and we would use the same steps that we followed in type 2 problem. So first we would be using the x coordinate that we know for the point of intersection, put it here. Then we would put in the y coordinate in here, and we would solve for s and t. Once we would get to know what is the value of s and t, we will sub that in here, and we will be simplifying that to solve the z value. And that z value will be this third coordinate of this point of intersection. Let's see how we get that. So x we are given as 0 is equal to 6 plus 1s is just s plus 2t. Y is also 0. We would put in negative 2 plus 3s plus 2t. We notice we can do elimination here because 2t and 2t is same values. We can also do substitution because we have two variables and two equations. I'm going to do elimination here. So for that, I have to subtract the second equation with the first equation. This cancels out. I'm going to be left with s minus 3s, which is minus 2s. And I'm going to be left with 6 plus minus 2, which is 4, is equal to 0. So I would have 4 plus minus is basically 4 minus 2s is 0. When I simplify it, I'm going to be able to get minus 2s is equal to 4. And this would give me s equal to 4 divided by negative 2, which is negative 2. All I have to do is just substitute this s into any one of these two equations. I'm just going to put it in the first one. So it would be 6 plus s I know is minus 2 plus 2t. I'm doing this is to solve for t value. So 6 plus minus 2 gives me 4 plus 2t is 0. When I move 4 here, it becomes negative 4 equal to 2t. So t would be equal to negative 4 divided by 2. That is a negative 2. It's by chance that we're able to get the same s and t value, but it's not that we will always get the same s and t value. When we simplify this further, we would be able to get s minus 3s, which is negative 2s, and 6 plus 2 gives us an 8 equal to 0. We move 8 on the other side, that gives us negative 8 equal to negative 2s. So s is equal to negative 8 divided by negative 2, which is equal to 4. Once we get the value of s, all we have to do is just substitute this s into any one of these two equations to get the value of t. I'm just substituting it in the first one. So s is 4 plus 2t. 6 plus 4 is 10 plus 2t is equal to 0. We're left with 2t equal to negative 10. So t is equal to negative 10 divided by 2, which is negative 5. And from here we get the value of s and t. Once we've got the value of s and t, all we have to do is just use this equation, substitute s and t in there, and get the value of z. And that z is nothing but this c value. So z is equal to negative 3 plus 0 times s is 4 minus 1 times t is negative 5. That would give us a negative 3 plus 0 plus 5. And finally, we would get a 2 value for z. So the point of intersection finally can be written as 0, 0, and this is how we end the problem. Type 4 problem is when we are given a line equation, r is equal to 1, 1, 1 plus s negative 1, 1, 0, and we are given a point P that is 1, negative 5, 9, and we are asked to determine vector and parametric equations. Let's first understand this with a diagram. Let's say we are given this line that is represented by vector r. Because this represents a point on this line, so let's call that point A. Therefore, the coordinates of this point will be 1, 1, 1. And we are given another point 1, negative 5, 9, called point P. As we need to determine the vector and the parametric equation of the plane, we have one direction vector that we get from the line. From the point, we make another direction vector going towards the given point P.
And using AP, we will find what is the second direction vector. So we can say AP direction vector is x2 minus x1, that is 1 minus 1, y2 minus y1, that is negative 5 minus 1, and z2 minus z1, that is 9 minus 1. When we simplify this, we would get 0, negative 6, 8. Since we've got the second direction vector, which is this one, the first direction vector is this one, and we know the initial point, we can use both the direction vectors and the initial point to write on the equation of the plane. So we would have the vector equation as r equal to 1, 1, 1 plus s negative 1, 1, 0, that's this direction vector, plus t, this is the other direction vector that we've got the coordinates here, 0, negative 6, 8, and this is how we get the vector equation of a plane. As we have the vector equation, getting the parametric equation follows the same process of splitting x, y, and z. So we would write down x is equal to 1 plus minus 1s, that comes from here, plus 0t. Because we have a 0, so we can rewrite this in simple terms as 1 minus s. That's it. Y would be equal to 1 plus s minus 60, and z would be equal to 1. Because it's 0s, we don't have to put s there, and this is 8t, so it's 1 plus 8t. So this is how the parametric equation looked like. And these were all the different types of questions that can be asked for vector and parametric equation of a plane.